Okay, this is a very brief story of how our project team adapted the 19th century glazing technology in the central dome of the Buffalo and Erie County Botanical Garden to address cold climate conditions. The story begins in England in the early decades of the 19th century. Napoleon is deposed, the Industrial Revolution is underway, it's an age of great optimism, and rich folk are commissioning newfangled conservatories from daring engineers to display tropical plants being gathered from all over Europe. They have cast iron structures, cast iron or wood glazing bars, and newly available plate glass set in linseed oil sealants. By the 1870s, the technology has matured and fabulously large glass houses are popping up all over Britain and on the continent. This is the Royal Botanical Gardens at Kew, just outside London. The technology worked very well in England because wages were low, making large maintenance staffs practical, but mostly because the climate is relatively benign. Yearly temperature swings stay within 80 degrees, or freezing temperatures are infrequent and usually short-lived. In this country, Lord Burnham, a company with roots in western New York, begins building similar structures. The Conservatory of Flowers was built in San Francisco in 1879. Although the system is the same, we had unlimited supplies of quality wood in North America, so the structure and the glazing supports are Gulf Coast cypress. The very famous New York Botanical Gardens was built by Lord Burnham just ahead of Buffalo's conservatory. It's the same design, but is approximately 1/3 larger. By 1900, the larger houses are built with cast iron structures, but the glazing supports remain wood, and the glass is still set in linseed oil pipes. It still works because the typical climate remains relatively temperate. Then, 100-degree temperature swings every year and long stretches of freezing temperatures. To make matters worse, the ebb and flow between freeze-thaw cycles can be a daily occurrence for months on end. Our original facility was a 2/3 version of New York with the same details, but here, the hothouse interior versus the frigid exterior led to horrific condensation and dramatic expansion and contraction issues. Too much glass broke, and the structural connections corroded. By the 1930s, the conservatory was rebuilt on the original foundation, but steel was substituted for cast iron. The cypress glazing bars were set wider apart, but the glass was still set in pipe. Unfortunately, the climate remained, the maintenance staff got much smaller, and the glass continued to break. After World War II, the boys at Lord Burnham talked the city into trying some new materials developed during the war. The wood glazing bars were replaced with aluminum extrusions. The glass was set in butyl rubber sealant. Although an improvement, the glass kept breaking while the maintenance staffs were essentially eliminated. Please note a section through the typical extruded aluminum glazing bar from this era. We believed the bedding shelf, that is the support for the glass, was too shallow, and we noted that the butyl sealant got rigid within a decade. The bar cap protecting everything from above imposed a point load on the glass. Unfortunately, aluminum has a spectacular expansion coefficient compared to the earlier wood material, and the hot, wet inside expands differently from the colder, drier outside, but it's restrained by the pointed edges of the bar cap, so the glass kept breaking. In many cases, very nasty shards of glass would fall out of place and threaten visitors below. When we began our project, the county had placed scaffolding over the walkways inside the dome to protect visitors from falling glass. Better detail could not be devised, the existence of the conservatory was threatened. We spent 2 years developing and testing alternative glazing methods that would allow the extreme movement inherent in the system. We needed it to perform longer, and we needed to be able to use safety glass in order to comply with modern building codes that require overhead glazing that will resist breaking in places of assembly. What we did was add a continuous aluminum extrusion that increased the bearing surfaces for the glass. We set laminated glass on preformed silicone strips, anchored the glass to the aluminum along the edges with wet silicone, and protected the assembly from UV degradation with a spring-loaded bar cap that prevents expansion and contraction of failure assembly. The silicone remains resilient indefinitely, but does not bond the glass to the system except along the glass edge, where it can be accessed and replaced should the glass break. Unlike butyl sealants, where old material must be completely removed before a new material can be applied, new silicone bonds to the old. The preformed strips set the glass in the ideal location every time and cushion it with potentially cold metal. Best of all, silicone can be applied in temperatures down to 20 degrees below zero, and it remains resilient in even colder temperatures. Its expected life cycle is 40 years. The installation is 12 years old now, and we've lost not a single piece of glass. Although we were not politically astute enough to get invited back to design the next phases, this cushion detail has become the basis for all subsequent glazing throughout the complex.